Okay, we are ready to start. Hello, everyone, and welcome one more Thursday to one more lecture of our Heterogeneous Systems course. Today, we are going to talk about a new parallel pattern about the sparse matrices. In reality, it's not only a parallel pattern, this is more like a type of data structures that can be stored in different ways, and also depending on the algorithms that we want to implement and use them, and depending on how we store the matrices, we will have different parallel patterns. I think it's going to be an interesting lecture. But before we start talking about the sparse matrices, let me very quickly remind you what are the parallel patterns that we have covered so far. Remember that we started with the parallel reduction. The reduction is a simple operation that reduces a set of values to a single value. And this reduction needs to have certain properties like associativity, commutativity, and an identity value. We said, or we talked also about the applications of reductions, and we saw that it's a key primitive for parallel computing. We discussed different ways of implementing reduction, but in the end, the most important thing was to try to minimize the divergence existing among the threads that are working together, computing the reduction. Because this way we can maximize the warp utilization, and this way we can achieve much better performance. The second important parallel pattern that we covered is histogram computation. As you may remember, a histogram is a data structure, probably a linear array that is composed by bins, and these bins have a counter that is associated. We are going to increment the counter every time that we find a new element that falls on the bin, either because it has an exact value or because it's in a range of values that are represented by the specific bin. Regarding the parallel implementation of histogram computation, one thing that we noticed is that we may have different threads that are executing together that want to update the same memory locations, want to update the same bins of the histogram. In that case, we will have a conflict, and the way of solving this is to use atomic operations. Even though atomic operations are costly because they serialize the execution, we also saw that there might be ways of optimizing the execution of these type of programs by using certain optimization techniques. And the most popular one for histogram computation is privatization, where we create multiple subhistograms that are later merged into a single one. The next parallel pattern was the convolution, a very important parallel pattern for different algorithms in image processing, video processing, or computer vision, and also very much used in the field of machine learning and artificial intelligence these days. As you may remember, when computing a convolution, what we normally do is applying a mask or a filter on each element of the input and perform some partial products. And finally, we reduce all these products before we store the final result on the output array. We discussed the 1D convolution, and we also talk about the 2D convolution and examples from CNNs. And one more thing that we explained in this meeting, was how to lower a convolutional layer into a matrix multiplication can even benefit more from the architecture of the GPUs and different optimizations that we can apply to them. And the parallel pattern that we covered in our previous lecture was the prefix sum or scan, also very important parallel primitive for many different applications. In scan, as you may remember, we also use an associative operator, same as in the parallel reduction. But in this case, the value of, we are going to have not a single output value, but a whole output array where each element of the output array is dependent on the previous elements of the input array. We discussed how to implement a scan. We talk about different ways of implementing, and in the end, the most efficient way of doing a scan is by using, on a GPU, is by using a hierarchical implementation where we first perform some operation per block. In this specific case, it's a scan add implementation in this slide, where we first perform the per block scan we then compute the scan operation for the partial sums in order to find what are the offsets that we need to add to the elements in the output array and obtain the final result. We talk about different algorithms, a couple of important algorithms to implement the scan at the thread block level and at the warp level as well, being the most popular and widely used these days, the Coggy-Stone parallel scan algorithm. Okay, I don't know if there are any questions from previous meetings. I will be open to answer the questions right now. I will, so feel free to stop me anytime if you have any questions over the course of this lecture. And also, if I see that there are any questions in the YouTube chat, I will also be glad to answer them. So now let's start talking about the sparse matrices, the way that we are going to store these sparse matrices in memory, and how we are going to use them to perform the necessary operations when we implement important algorithms. Let's first define what is a sparse matrix. Probably all of you already know this, but probably all of you are even more familiar with dense matrices. Dense matrices can be two-dimensional data structures. They may have also more dimensions as well, but we will consider the case of two-dimensional matrices today, where a dense matrix is a matrix where most of the elements are not zero. That means that most of the elements are useful for computation. However, in sparse matrices, it happens exactly the other way around. Most of the elements are zero, and only very few elements of the matrix are really relevant for computation. As we are going to see today, these are very important and widely used in many important applications. And the fact that the matrices are sparse, the fact that most of the elements are zero, it's going to entail important challenges when operating using these data structures, but also has some opportunities that we should try to take. The first of them is that we don't need to allocate the space for zeros, so we can compress the sparse matrices, and this will save significant amount of memory capacity. We don't need to load zeros because we are not going to use them for computation. They are essentially useless. And this means that we save memory bandwidth because we don't need to read them from memory. And we are also saving computation time or execution time because we don't need to compute with the zeros. We already know if we are performing a matrix multiplication, for example, we already know that multiplying by zero will produce a zero. So there is no point in using the zeros for computation. And matrices, as I said, these sparse matrices are widespread today. We can find them in important modern applications like recommender systems, graph analytics, and neural networks. We are actually going to cover graph analytics in a later lecture, and we will see how important sparse matrices are for them as well. And it turns out that the matrices in the real world have high sparsity. Here you can see a couple of examples from Facebook and YouTube. So it's very important to compress the matrices in an efficient way, because this is going to save storage and also may save computation and facilitate computation as well. So that's why we are going to talk today about several sparse matrix compression formats that are important, and all of them have their own pros and cons, as you will see. Some of these storage formats for sparse matrices can be the coordinate format, COO, the compressed sparse row format, CSR, the ELLPACK format, ELL, and the Jack diagonal store, the JDS. And there are more. We are going to talk even about a couple more today. When deciding what's the right compression format for the problem that we are dealing with, there are several design considerations to take into account. The first one is the space efficiency. That is how much memory is consumed, because in the end, we don't want to waste memory, right? So there's no need for storing zeros, and we may eventually want to store some of the zeros, but that's because we are going to save space in a different way, or because that's going to enable like more efficient computation. We will see some examples of that. Another important consideration is flexibility. How easy is to add or reorder elements. Another consideration is the accessibility. How easy is to find the desired data, the specific elements that we want to find, or the place where they are located, the row and column. And also, it's important to think about how good are going to be, or the algorithms implemented using these storage formats. And one of the things that it's important here is the type of memory access pattern, right? Because that relates to how efficient is or access to the memory of the GPUs, whether the accesses are coalesced or not, essentially. And one last thing is the load balancing, because we want to minimize the control divergence. We want to maximize the warp utilization, as you know, in order to achieve higher performance. And we will see that load balancing is challenging as well when computing with the sparse matrices, because in different parts of the matrix, we may have very different numbers of non-zero elements. So in the end, as I said before, choosing a format depends also on the computation that we want to apply on the matrices, and also on the hardware that we are using as well. But we will mostly focus today on GPUs. Over the course of the presentation, and especially the first part, we are going to talk mostly about one key algorithm for sparse matrices, that is the sparse matrix vector multiplication, or SPMV. In a sparse matrix vector multiplication, or SPMV, what we do is multiplying a matrix, a sparse matrix, by a dense vector, and we will obtain a dense vector as well. Now, let's start discussing how we are going to store these sparse matrix in memory, how we are going to compress it, and then we will see how we distribute the computation when it comes to multiplying by this vector. The first format that we cover today is probably the simplest one and most and easier to understand. If this is our original matrix in dense format representation, one thing that we can do to store only the non-zero elements is to store the value of each non-zero element and create a tuple, a 3-input tuple that contains the value, the row, and the column where this value is placed in the dense representation. For example, this one here is the element 0, 0, so that's what we keep in memory. Or this element here, this 7, is element 0, 1 in row 0 and column 1. So that's what we do in the coordinate format, or COO. Now let's discuss, or let's think about how to implement an SPMV operation using this format. In SPMV, as you already know, we have to multiply this sparse matrix by a dense vector. And this is how our sparse matrix looks in memory. Remember that in memory, we store everything, also the matrices, in a linear manner. So that's how we are representing the matrix, or storing the matrix in memory. So in the first parallelization approach to this SPMV algorithm using COO is to assign one thread per non-zero element, because we have all these 3 input tuples in memory. We can simply assign each of the threads of our kernel, of our grid, to consecutive elements, right? So in the end, this thread here is going to multiply this one by this first element of the dense vector, and store or accumulate the result in this element of the output. And for this thread here, this one is going to multiply this element 7 by this element here, and also store in the same, or accumulate in the same element of the output. So what's the problem here is that we are going to have several threads, maybe a few, maybe many, updating the same element of the output. And in order to do so, because these threads are likely running concurrently, we will need to use atomic operations to avoid data races and make sure that we obtain the correct result in the end. And this is how the code looks. As you see, it's a relatively simple and compact code. The first thing to do in this code is to obtain one index, which is the global index of each thread. And this is the index of the element in the matrix. This matrix represented with the COO format is the index of the in the compressed matrix where the thread will find the corresponding value of the matrix. Notice that we first read the row, the column for this element, and then finally the value. We also have to access the corresponding element of the tens vector, perform the multiplication, and after that, when it comes to accumulating the output vector, we will use an atomic operation. Why is that? Because we will probably have other threads operating on the same row of the matrix, and these threads might be executing concurrently and updating the same element at the same time. So that's why we need the atomic operations here. You know that atomic operations are costly, serialize the execution. We already discussed in previous lectures some ways of getting rid of some of this serialization or optimizing the execution of the atomic operations in some way. And one of the ways that we could apply here is using coalesced atomic operations. And this way, we can at least reduce the overhead of using the atomic operations by a little bit. But yeah, in the end, same as the other formats that we are going to cover in this lecture, COO has trade-offs. There are some advantages that are clear. For example, it's flexible in the sense that it's easy to add new elements to the matrix because the non-zeros can be stored in any order. We don't really need to sort the elements of the matrix in any way because every element of the matrix is accompanied by its row and column. It's in terms of accessibility, COO, it's good because giving a non-zero is easy to find the row and column. So if you just go grab some element, you can easily find what's the row and the column of this element because it's stored in the same tuple, in the same position of the corresponding row or column index array. And also the implementation of SPMB when accessing the sparse matrix store with the COO format has coalesced memory accesses, which is very good, as you know, to take advantage of the memory bandwidth. And also another good thing is that there is no control divergence. If we have two threads in the same warp, each of them operating on a different element of the matrix, they can execute at the same time. There's no control divergence. The only problem is that we need to use atomic operations, and there is where we are going to have the serialization. And actually, that's one of the disadvantages. The other disadvantage is in terms of accessibility, that given a row or a column, it's hard to find all non-zeros in that row and or in that column. Why is that? Because the non-zeros might not even be sorted in any way. So we need to search over the whole compressed matrix to find all non-zero elements corresponding to a row or a column. Okay, let me know if there are any questions. Yeah, we have already covered our first sparse matrix format, compression format for sparse matrices. Now we are going to talk about the second one, the compressed sparse row, which is probably the most popular one. One reason is that it provides high compression ratio, as we will see, higher than what the COO does, and also that's probably one of the reasons why CSR is used by many state-of-the-art libraries and frameworks like Intel MKL, Gunrock, and many more. So in the compressed sparse row format, in CSR format, what we do is storing the non-zeros of the same row adjacently and have an index to the first element of each row. So this index in the end represents kind of a pointer where we keep the exact position of the matrix where the elements of a row start. So for example, in the original matrix, we have that in row 0, we have only 2 elements, 1 and 7. We store these 2 elements next to each other. We also store the column where each of the elements reside. But now, because all these consecutive elements belong to the same row. We don't need to store the row index for every single element. We can just store the row index for or a pointer to where the row starts that is common to all elements of the row. So this row pointer here, value 0, indicates that in the position element 0 of the column index array and the value array, the elements of row 0 start. These 2 here indicates that in position number 2, the elements of row 1 start. These 5 indicates where the next row starts, and so on. So now let's think about how to implement SPMB operation using the CSR format. So the way that we are going to operate here, the parallelization approach, is to assign one thread to a whole row. If we do that, the good thing with respect to COO is that we don't need to use atomic operations anymore. Why is that? Because all the multiplications and additions that are needed to calculate this element here will be performed by the same thread, that thread that is assigned to this first row here, because that one will multiply all the elements of the row by all the elements of the, or the corresponding elements of the input vector, and this way obtain the result that is directly written here without atomic operations. So this is the possible assignment: one thread working here, one thread working in the next row, this thread working in the next row, and so on. And they start iterating. In the first iteration, they perform the first multiplication and accumulate. Second iteration, they perform the second multiplication and accumulate. But notice that we already see some divergence due to load imbalance. Why is that? Because this last row of the matrix has only a single element. So in the second iteration, the thread assigned to that row directly retires, right? It becomes idle. And then when we continue with the execution, more threads will start retiring. And this shows one of the key disadvantages of this algorithm or this format, the fact that we have quite a bit of load imbalance. So we are going to have significant warp divergence. And also there is another drawback here. Observe that threads, consecutive threads that are operating, computing consecutive rows, they are also accessing memory at a certain distance, right? And this distance is a stride, and this stride makes that in order to satisfy all the memory requests from all threads belonging to the same warp, we will need multiple memory transactions. So in the end, the memory accesses are not coalesced, and due to that, we are not going to be exploiting the bandwidth at its best. Here you can see the code. It's a little bit more complicated than the code for the COO representation. Now, instead of having an index for each individual thread and an index for each individual element that is assigned to each thread, here we have one index for the row that is obtained from the global index of each thread, and then each thread goes over all the elements that belong to the same row. For each of the elements, it finds the column index, it finds the value, performs the multiplication, and accumulates in some variable that is later stored in the output array. So as you see here, we don't need atomic operations here, but as we have already discussed in the previous slide, we will have load imbalance and we will have uncoalesced memory accesses. There are probably more optimizations that we can apply to this code here. As you see, it's a pretty simple code, pretty straightforward implementation. And we know already some ways of optimizing our code, as we have seen in previous lectures. One thing that we could do here is storing the whole input vector, which is this dense vector that is essentially accessed by all threads of a block. Store this vector in shared memory is one possibility, or if it doesn't fit completely, we can store chunks and perform several iterations in an outer loop where we first load a chunk of the input vector, perform the corresponding multiplications and store and so on. CSR also has trade-offs, as we are discussing. It has advantages, space efficiency. It's more efficient in terms of space than COO, because the row pointers, the array of row pointers is small than the array of row indices that we need to use in COO. In terms of accessibility, given a row, it's easy to find all known zeros of that row, because we have already seen that all elements of a row, or non-zero elements of a row, are stored consecutively. There are no need for atomic operations, because each thread owns its own output. But it also has some disadvantages, right? So in terms of flexibility, it's hard to add new elements to the matrix. Why is that? Because if we want to add a new element to row 0 or a new element to row 31, the problem is that we will need to move all the later elements to find the right place or let's say freeing the right place for these new elements, right? So that's it's going to be pretty costly in terms of data movement and computation time in the end. In terms of accessibility, given a non-zero, it's hard to find the row, and given a column, it's hard to find all non-zeros. Yeah, I think that's also pretty obvious if you look at the example that we showed before, how the data elements, the non-zero elements, are stored. The next disadvantage is that the memory accesses are not coalesced, as we already discussed, and also there is control divergence. Let's see if we can improve these the characteristics of this CSR format in some way, proposing other formats. But before that, let me also introduce you to the, say, sibling format of CSR, which is CSC. The only difference between CSR and CSC is that instead of having an array of row pointers, we have an array of column pointers. So the idea is the same, but instead of storing the elements by row, we store the elements by column. So that's why we have these column pointers, and we store the values and the row where each value is stored. This essentially has very similar trade-offs, but depending on the algorithm, depending on the way that we want to go through the data elements, we may prefer this CSC format. So the next format that we are going to discuss is this ELLPACK format that is going to solve some of the issues with CSR. So this is our matrix, same as before, and same as in CSR, we are going to group the non-zeros by row. So again, we are storing all all elements of the same row consecutive in memory, and we keep the value, and we also need to keep the column where the value resides. But now one difference is that we are going to pad all these rows so that they all will end up having the same size. And that's going to be pretty useful in some ways, as you're going to see. But there is one more novelty as well, is that we are going to transpose the matrix. So instead of storing it in a row major layout, as we usually do with matrices, we are going to store it in a column major order, as you see. So all these elements are going to store consecutively in memory, and then we will have then the elements in the next column, and then the elements in the next column of these matrix representations that you see here, and so on. So the way that they are going to look in the linear memory is same as if we transpose the matrix, right? And that's why we first find in memory, we will first find this 1, then this 5, then this 2, then this 6, and so on. And now when it turns to computing SPMB, the way that we are going to parallelize is again by assigning one thread per row. But observe that when these threads here start the computation, they all are accessing elements that are stored in memory in consecutive memory locations. So what this means is that if these consecutive threads belong to the same wire, they are accessing accessing memory in a codeless manner. So we are minimizing the number of memory transactions that we need and essentially improving the bandwidth utilization. So this would be the first iteration. This is the second iteration, and now observe that some threads start retiring because I mean, not all rows have the same number of non-zero elements, and the execution continues, and more threads retire. This is the code corresponding to this SPMB implementation using ELL format. It's pretty similar to the implementation of CSR. What is different is the way we index the elements that are in this ELL format, but that's simply because they are stored in a different way. But other than that, the computation is pretty similar. Again, no atomic operations, and again, one thread assigned to each row. And this format has also its own trade-offs, advantages and disadvantages. In terms of advantages, we can add new elements as long as the row is not full, because we are padding the rows, right? So that all rows have the same size. So if one row is not complete, there will be some empty memory positions that we can use to add new elements that belong to the corresponding row. In terms of accessibility, given a row is easy to find all non-zeros. Given a non-zero is easy to find the row and the column. So another advantage, as we have seen, is that the memory accesses are coalesced, but there are also some disadvantages. In terms of the space efficiency, this format is not the best one because we are padding all the rows, so there is an overhead extra memory capacity that we need to use. In terms of accessibility, given a column, is hard to find all non-zeros, and the implementation of SPMB has control divergence, as we have seen. So let's try to improve, optimize this format a little bit more. We can go for a hybrid ELL plus COO format, where what we do is creating or storing the matrix in the ELL format as we did before. But now we are going to somehow cut the rows so that in the ELL format, we are only going to store some elements of the row. While for those matrices that are, so those rows that are too long, for example, this green and this pink row in this particular example, those excesses of the row, we are going to store them separately using the COO format. So for all these elements that belong to the, let's say, the last part of the green and the pink row, we are storing them in COO format, while the rest of the rows are stored in the ELL format. So this format, or this hybrid format, has some extra benefits. The first one is that with respect to ELL, we are using less padding, because now, as you have seen in the previous slide, we don't need to store all these blank elements here, all these empty elements here. It's flexible in the sense that we can add new elements to any row. So even if one row is complete in the ELL part of the matrix, we can always store new elements in the COO format. And it shows less control divergence. Why is that? Because this part stored in the ELL format is pretty dense, as you can see. And because it's pretty dense, when we assign one thread to each of the to each row, they will be working most of the time. So this way we are reducing the control divergence. And let's discuss one more. This JDS. This is the matrix that we are going to consider in this example. And again, we start in a very similar way as in CSR and as in ELL. In this case, we store elements belonging to the same row together. So we group the elements by row. But now, one thing we do is sorting the rows based on what's the number of elements in the row. One problem of doing that is that we also need to store in some way the row that is actually placed at a particular position. For example, the longest row in this matrix is row 1. Now, after sorting the rows, it's going to be placed at the beginning of the compressed matrix. But because this one is not anymore row 0, we have to also store in another array what's the row number. In this case is row 1. And then also, same as in ELL, we are going to store these in column major order. We have already seen that one good thing of doing a column in major order is that we have call-less memory accesses. So this is how the matrix is going to look in memory: the column array, the row array, and the value array. And there is one more thing that we add here is an iteration pointer. In the end, what this pointer here is going to do, and unlike the pointers that we the row pointer that we use in CSR that points to the beginning of one row, here we have a pointer that points to the exact position where threads will start computing in each iteration of the algorithm. Because we are going to assign, same as before, threads to rows. Each thread, or the threads that are computing, need to know exactly where to go when performing the next iteration of the algorithm. That is, when moving to the next element of the row. Notice that we didn't need this iteration pointer in ELL, because in ELL we are padding all the rows. And what that means is that in all iterations, we have the same number of elements, even though some of the elements will be pad, will be just zeros that we don't really need to operate on. But yeah, that facilitates for the threads the way of finding the corresponding elements of the rows that they need to use. Because here in JDS we are not padding. We need this iterations pointer. So in the first iteration, again, we assign one thread to each row. In the first iteration, as you can see, all memory accesses are coalesced. And also, one advantage of this format is that we managed to reduce the control divergence as well. Why is that? Because the threads that are dropping out after each iteration are threads from the end. Remember the example of the parallel reduction that we discussed in a past meeting, and we also very briefly reviewed in the beginning of this lecture. And the most efficient implementation of the parallel reduction assigns threads to the elements of the input array in a way that iteration after iteration, the threads that retire are the higher indexed threads, and all of these belong to the same warp. And when they start retiring, complete warps retire, and this way we minimize the divergence inside each warp and maximize the warp utilization. So we are doing something similar here as well. When threads start retiring, and those threads that start retiring are those that are closer to the end, because those are the shorter rows. When these guys start retiring, they all belong to the same warp, and the threads that remain belong also to the same warp, and this way we maximize the utilization. So the computation continues, and this would be the next iteration, and so on. So trade-offs, advantages. It's good in terms of space efficiency because there is no padding. It's accessible for a row when we are looking for the non-zero elements of a row. The memory accesses are coalesced, and we have also seen that we minimize the control divergence. However, it also has some disadvantages. In terms of flexibility, it's hard to add new elements to the matrix for the same reason as the previous formats as well, like the CSR, for example. And in terms of accessibility, given a non-zero, it's hard to find the row, and given a column, is hard to find all non-zeros. So we see that all formats have their own pros and cons, their own advantages and disadvantages. And in the end, we want to choose the most appropriate format for the specific problem that we target, the specific algorithm, and also the specific matrix. We are going to see some examples, some more examples of that in the remainder of this lecture. One thing that is common to all the formats that we have presented until now is that they all have difficulties or issues in terms of accessibility, and also one additional overhead that all these sparse matrix formats represent is that indexing is costly. Why indexing is costly? Because in the end, when we are performing the SPMB operation or a sparse matrix multiplication, for example, we need to find where the specific elements of a row reside in memory, right? Because they are compressed, we don't have zeros, so accessing elements, let's say accessing element row 100, column 101 is not so straightforward anymore, right? We have to check other arrays, like for example in CSR, we have to go and check the pointer array, and then after that perform an indirect access to the value and the column. So there is an indexing overhead. And for example, in a sparse matrix vector multiply, indexing every non-zero element of the sparse matrix is necessary to multiply with the corresponding element of the vector. And as I said, this requires to go in CSR, for example, to go to the array of row pointers, go to the specific row number, and then find what's the pointer to the values and the column arrays that store the element we are looking for. And something similar happens as well in a sparse matrix multiplication, where we need to do index matching for every inner product between the two sparse matrices. So indexing is expensive, and ideally we should find some, or we should design, or we should be able to design some sparse matrix format that is more lightweight in terms of efficiency, while still being good in terms of space efficiency, and improve the performance of our codes in that way. Actually, from one recent work from our group, we have this performing, so we have evaluated what's the cost of performing indexing in three important sparse matrix algorithms: addition, SPMB, and SPMM. This is the bar for CSR. These are speed up results, where we show what would be the potential speed up that we could achieve if we were able to get rid of all the cost of indexing, right? So we have obtained these numbers here that clearly show that a lot of the execution time of these sparse matrix algorithms is due to the indexing cost. And observe that we can almost 2.81 times faster we could be if we were able to minimize or completely remove the cost of doing indexing. So that's what we targeted as our goal in, as I said, one of our recent works, SMASH, that I'm going to very briefly present or introduce today. Again, let's recap about the limitations of existing compression formats. The general compression formats are optimized for storage, but they make very difficult, very expensive to discover the positions of the non-zero elements, as we have discussed before. And there are some specialized formats. We are the ones we are presenting today, but even more specialized, like for example, formats that focus on storing the diagonals, and this way they can be more efficient, but they are also specific to certain matrix structure. So that what happens with them is that they have narrow applicability, so they are not useful for the general case. So the question here is, what is an ideal compression format? An ideal compression format is a format that minimizes the indexing overheads, that can be used across a wide range of matrices and sparse matrix operations, and also enables high compression ratio. And that's what we propose in the SMASH paper, one of the works by Konstantinos, a PhD student in the Safari group, where he proposed a bitmap-based compression format. Let me explain you quickly what's this, the key idea of this SMASH project. The key idea is a hardware-software cooperative mechanism that enables highly efficient sparse matrix compression and computation, and also is general across different types of matrices and different types of sparse matrix operations. As I said, it's a hardware-software cooperative mechanism, so it has a software side, which is the compression format that we propose based on a hierarchy of bitmaps, and the hardware unit that is added to the CPU in the case of our paper, but this could be also applicable to other devices like GPUs. And this hardware unit scans the bitmaps to accelerate indexing. The way to communicate the hardware with the software is by using a specialized ISA. But today we are going to focus on the software compression scheme, because it's we are talking about software compression schemes and how they can be used in a general purpose architecture like GPUs. So in terms of software, as I said, we propose a compression mechanism or compression format that is based on a hierarchy of bitmaps, and it encodes the positions of non-zero elements using bits to maintain low storage overhead. Let me show you an example. The idea is to encode each block of the matrix that contains at least one non-zero element, encoded by using the bitmap. So on the left, we have our matrix. On the right, we have the bitmap. This is our first non-zero block, which means that some of the elements in this block are non-zero. And I want to emphasize the fact that this is not an individual element. This is a block of consecutive elements, for example, one cache line. And each non-zero block has a bit associated in the bitmap. This is another non-zero block and the corresponding bit in the bitmap, and these are two more. So one problem that we have now with this bitmap, even though these are just simple bits, either 1 or 0, is that we may have many non-zero blocks and many blocks in total in our matrix, right? That depends on how large are these blocks. So what we can do here is applying the same idea to the bitmap as well. So we are going to encode this matrix using the bitmap, but now we can also compress this bitmap using another bitmap. So we can use, in fact, a hierarchy of bitmaps. So for example, if this is our matrix, what we will have is an array of non-zero values. As again, let me clarify, these are not only non-zero values, these are non-zero blocks which contain at least one element that is non-zero. And then we create the bitmap. So observe that we only have 3 non-zero blocks here. So we only have 3 bits in the bitmap that are equal 1. And now, because this bitmap 0 is relatively large still, we can compress it and obtain some bitmap 1. And maybe even want to compare, we even might want to compress even more and have another level of the hierarchy of bitmaps. So as you can see, we are applying here from bitmap 0 to bitmap 1, we are applying a compression ratio 4:1. From bitmap 1 to bitmap 2, we are applying a compression ratio 2:1. But these are also configurable. So depending on the specific matrix that we want to compress, we may want to use different compression ratios for the bitmap, same as we may also want to use different sizes for the blocks of non-zero elements. So now, when it comes to finding a particular element in the array of non-zero values, it's as simple as going through the bitmaps from the higher levels of the hierarchy to the lower levels of the hierarchy. And this way, we will find what's the what's the exact position in the matrix of these non-zero blocks. So this proposed format is efficient in terms of storage. We are going to see a comparison to CSR in a few slides. Provides fast indexing. We are minimizing a lot the overhead of indexing. Is not anymore as complex and costly as in CSR, for example, and it's also hardware friendly. And actually, it's hardware friendly. And in the paper, we explain the necessary hardware additions. We are, as I said, I'm not going to cover them today because I want to focus on the compression part of the proposal, but you can find all the details in the paper. And actually, you can also find interesting evaluation results. Here you can already see some speed ups that SMASH provides with respect to other two formats, CSR and BCSR, up to 44% performance improvement with respect to the CSR representation. So significant performance improvement over state-of-the-art formats. And even you can find this evaluation in the paper, even the software-only SMASH without adding any extra hardware and by let's say accessing the bitmap hierarchy in the CPU itself, we can outperform the CSR representation by around 10% for some of these benchmarks that we use. And how about the storage efficiency? Well, this is the list of matrices that we used in our work. As you can see, they all are sparse, but the amount of sparsity depends. Differs from one to others. We have some matrices that are highly sparse, only 0.01% of the elements are non-zeros, and we have other matrices that are a little bit more dense. But yeah, this one, for example, like 8.79% of the elements are non-zeros. And if we compare the storage efficiency of CSR and SMASH, what we see is that for the most sparse matrices, CSR is more efficient, but for the rest of them, SMASH is more efficient. And by the way, notice that the y-axis here is in a logarithmic scale. So even though you may see that the gap here is not that long, in reality it is. It's significantly more efficient in terms of storage and compression. So anyway, if you want to learn more about this proposal, and I would recommend you to check the paper. You can access everything from here. And before we finish today's lecture, I want to talk a little bit more about how we can optimize these kind of operations. And you may remember that one of the, let's say, most recent and fanciest execution units that GPUs have these days are these Tensor cores that are optimized for deep learning, machine learning, and artificial intelligence, and so on. They are especially good at executing operations like convolutions, matrix multiplications, etc. So these Tensor cores are originally designed for computation of dense matrices, but we wanted to think whether we could somehow use them and take advantage of them when operating on sparse matrices. And that's one proposal from our group as well, from former PhD student Orestes, who created this T-sparse implementation of a sparse matrix multiplication that I'm going to briefly introduce today. Before we go into the details of T-sparse, let me very quickly remind you what a Tensor Core unit does. The Tensor Core units essentially multiply small tiles. The typical size are 16 by 16 elements, and they compute one of these. Either they obtain a subtile or a submatrix D from three input matrices A, B, and C, or they multiply A and B and accumulate in the output matrix C. So this is the pattern that they execute. They operate in half precision, 16 bits. The result is typically stored in 30 bits. But this is more or less how they look. And as I said, they multiply small tiles, and in the end, when we want to use them to perform a matrix multiplication, for example, we have to orchestrate the way that we offload the computation to the Tensor core units, fragment by fragment, as you may remember from the lecture where we talked about Tensor core units and about the implementation of the dense matrix multiplication. But now we want to see, or we want to discuss, how these Tensor core units could also be used to perform a sparse matrix multiplication. So in order to do so, we are going to propose a new matrix storage format as well. We are not actually going to propose a new one. You will see that it's proposed by a previous work. But what we are going to do is using this storage format to leverage the Tensor core units in an efficient way. Remember that some of the sparse matrix representations that we have presented in today's lecture focus on compressing individual elements. Like, for example, in COO, we only store the values that are non-zero, and we store the row and the index of each value. And we have also just discussed the smash compression format, where instead of storing individual elements next to each other, we store these non-zero blocks that contain at least one element that is non-zero, and then we index the blocks by using the bits in the bitmap. Now, in the T-sparse, we are going to use also a bitmap format, but as you will see, this bitmap format is different from the bitmap format in Smash. So let me very quickly remind you again, in Smash, we have blocks of non-zero elements, and we encode these blocks of non-zero elements with ones in the bitmap. While in the bitmap format that we use in T-sparse, what we do is creating the bitmap for different tiles. So what we are doing is dividing the whole matrix into tiles of the same size. As you see, these tiles here are two-dimensional, and then we create a bitmap for each of the tiles. For example, this is the bitmap of tile 0, and it's 0, 1, 1, because the elements in tile 0 are 0, 10, 15, 0. So 2 of the elements are 0, 2 of the elements are non-zero, and this is why the bitmap of tile 0 looks like this. Then we have the bitmap of tile 1, tile 2, and so on. And we will only store those tiles that have at least one element that is non-zero, like 0, 1, or 2. However, we won't store anything for this tile 3 because it's completely empty. It's full of zeros. Another thing that we have to store is an index. It's kind of a tile pointer that points to the exact place in the element arrays that where the elements of a tile start. So in this case, these two elements, 10 and 15, belong to tile 0. So the place where these two guys are stored is given by this index 0. The next index corresponds to tile 1, this element. So it's this index 2 goes directly to this element 20. That is the only element that is non-zero in tile 1, and so on. And as I said, we are not going to store anything for those tiles that are completely empty, like the tile 3. And this is why we also need to keep the coordinates of the tile in the dense matrix. So we need to know that this is tile 0, this is tile 1, this is tile 2, and so on. So this is the bitmap format that we use. And now each of these tiles that we are defining, we are creating, are the tiles that we are going to use to fit the tensor core units. As you remember, a tensor core unit performs a matrix multiplication of two small submatrices or tiles and stores the result in an output tile. In the TCU terminology, these are called fragments, as you may remember. So the way that we are going to map these tiles onto the tensor core units is in a similar way as this. We're going to use 16 by 16 large tiles, let's say, but then internally in each of these 16 by 16 tiles, we are going to use two tiles of 8 by 8 elements each. This is a way of being able to reduce the granularity of the tiles, because if we have larger tiles, we may have too many zero elements in them, and we may be storing bitmaps for tiles that are almost empty. So it makes sense to use smaller tiles so that we can also get rid of more tiles that are full of non-zero elements. And one other important observation here in the way that we map the computation onto the tensor core units is that we are not using the whole tile of the tensor core unit. We leave this part here empty and we leave this part here empty. We cannot place other tiles here for computation because otherwise they would also participate in the multiplication of this tile here and they would produce wrong results. So that's one issue that we have to solve by using only two of the four possible 8 by 8 tiles that we may have in one of the 16 by 16 tiles of the tensor core units. But even though we are somehow wasting some of the resources, the tensor cores are extremely efficient. We are going to show that, we show that in our work, but we have also seen that in previous works as well, such as this one that we discussed briefly in a previous lecture. You may remember when we talk about the reduction operation. Another challenge that we have to solve in this sparse is how much memory we want to allocate for the output. In the end, when we have two sparse input matrices, we don't really know how many elements, how many non-zero elements the output matrix is going to have, right? So this requires that we somehow figure out what's going to be the number of elements of the output matrix and how much storage space we need for the output matrices. There may be many ways, many solutions for this. One simple solution would be to use an upper bound to allocate much more memory than what we are really going to need in the end. But in this sparse work, we prefer a precise method. And in the precise method, what we do is, first of all, counting the number of elements that the output is going to have. And the way of doing this is by using the bitmaps. Good thing is that the bitmaps are smaller than the matrix, than the elements in the matrix, because bitmaps are just composed by bits, zeros or ones. And but these bitmaps give us a precise location of the elements in the two input matrices and also in the output matrix as well. So that's why we have this counting kernel that is executed before the multiplication kernel, because with the counting kernel that multiplies the bitmaps, we can find the precise amount of memory that we need to allocate for the output. And then we go to the multiplication. When we go to the multiplication, one thing that we have to do, these are all whole A, B, and C. So A, B, the two input matrices and the output C matrix. As you see, they are divided in tiles. And so the first thing that we have to do is checking the tiles of A and B and see which of them match, right? Because, for example, here we have in B a tile that is a non-zero tile. It has some non-zero elements, but the corresponding tile of A is completely zero. So we don't need to perform this multiplication. However, we find a match here among this tile 1 of matrix A and this tile 1 of matrix B. So these two we will multiply in the tensor core units. Here we also have a match, and here we also have a match. And by using a sorting operation, we create a list of tasks, and these tasks are essentially multiplications of tiles that are assigned to the available tensor core units. So here, as you see, these first three are going to be assigned to the tensor core unit 0, the next ones to the tensor core unit 1, and so on. And we place them in the right fragments before performing the multiplication. So here we have this first task that multiplies tile A1 and tile B1. So we place them in the corresponding part of the tensor core unit. Then we do the same for these two as well, A3 and B3. So A3 is here, B3 is here, and then we go to the next iteration. In the second iteration, we place this A4 here, B4 here, and so on. And after having performed this multiplication, we will accumulate that what this plus sign represents, and this way compute, perform all the tile-wise multiplications that are necessary to obtain the correct results in the output, in the output matrix C. And finally, after we are done with the multiplications, and the accumulations as well, we obtain the tiles of the matrices. This is one of the tiles of the output matrix. This is another tile of the output matrix. And now for these guys here, we also have to create the bitmap, right? Because this is the storage format that we are using. The way of generating the bitmap is relatively straightforward while using one of the warp-wise primitives that we already presented in a previous lecture, and is this ballot function. So by using ballot, we can compute the bitmap for each of the tiles of the output matrix, and separately we will store the non-zero elements of the matrix as well. So if we take a look at the speed up of this proposed method, we see pretty nice results for most of the matrices that we tested, and in comparison with let's say most up-to-date, most powerful state-of-the-art implementations of sparse matrix computation. Here we compare to the QSparse library, to CUSP, which is another optimized library, R-merge2 and NSparse. And we also compare to an implementation of our method that doesn't use the tensor core units. This is our way of showing that using tensor core units, even though we might not be using them fully, right? Because we are operating on sparse matrices, but still the method itself makes sense, and the usage of tensor core units, it's more efficient than using the regular compute unit. So as you see, so this plot presents the speed up of T-sparse with respect to the rest of methods. We see that the comparison is favorable in terms of geomean for all the methods. Only in a couple of matrices, there are two methods that are more efficient than our T-sparse method. But other than that, we see that T-sparse is pretty efficient in most of the cases. And as expected as well, it's more efficient when the tiles are a little bit denser, right? Because this way we could be making use of more SIMD lanes inside the TCUs. But if you want to learn more about this T-sparse method, I would definitely recommend you check our paper. There is also an archived version, and you can also access the code that is publicly available in the GitHub of Orestes. So this is all for today. My last comment is just to recommend you to check chapter 10 in the Programming Massively Parallel Processors book if you want to learn more about the sparse matrix computation and about sparse matrix compression. So thank you very much, guys, for your attention. Let me know if you have any questions. I think there are no questions in the YouTube chat. If you have any question, please let me know. And if not, I guess we are done. We are done for today. Okay. Yeah. I guess we are done. Yeah. Thank you, guys, for your attention, and thank you again, everyone as well in YouTube.